think we were back to the cell. It does look like most everybody's here, by the way, so good news there. And on we go. So I just sent you another one of these PowerPoints from this Marib series that I've been using for the cell. This is where we're going to continue. And I will let you know when we reach the point of these cell adhesion molecules that hold the cells together. Once we're done with those, that ends the first exam material. I had a couple of the occasional. See, this is the kind of inquiries I get. Is the test open book? Short answer: no. Unless otherwise stated. You know, if it was an open book test, you don't want an open book test. Trust me. Everybody, oh, I want an open book test. Here's the default. Everybody, they say, oh, it's open book. I don't really have to book it for this. And you see, when I do open books, there's time limit. You know, and I mean, then it's like you're scrambling. So it's all about, you know, you have to prepare and organize and all that stuff. I got 50 minutes and I've got this. Well, I could just look it up on my phone. To that end, we have all of my classes of this group, save the Wednesday afternoon, which has 13 people in a large classroom. Everybody else is packed. So what I have the same exam, it's going to be in different colors. Each one of those exams, whichever one you get, I just flip the questions around. It's not. This is not an accusation. There's an old saying: it's not only impropriety; it's the appearance of impropriety. That's the day that they'll be walking, people, important people around or the classrooms, which they do occasionally, and they kind of look in and they see, people, and because you can't help yourself. I was lucky. I was the guy they were cheating off of. Yes, sir.
Is the test on paper?
Paper. Bring your number 2 mechanical pencils, Scantron, bubble sheets, whatever the heck you call them, all that type of stuff. Yes, you can write on test. The whole idea why you ask that question is because you can make notes on the test, and then you put your name on it, and you'll be able to get that back and look at it. We do not review tests in class. Okay. If you want to make an appointment and come see me during office hours or some mutually convenient time, then we review your test, or a group of you. It will be novel to actually have someone. And I don't tell tales out of school, but that means so far in the collection of all these classes, the first question I got that isn't something like how do I spell that, or like is it a test on paper? I'm not making light of that. It's a good question. Okay, if someone asks me a question in class about the subject material, it'll be novel. Mutual participation stimulates discussion. Proactivity. I mean, and a lot of people are not comfortable because they don't want to stick out in the class. Do me a favor, get used to being, you want to establish an identity, not a negative one. I'm good. I had the whole negative ones down. I was the one raising your hand and the teacher ignored. I don't want to talk to you. That's my life in a nutshell. Very good. Lipid bilayer. Naturally, you throw phospholipids in, they make a bilayer. It's great. Terms you need to be familiar with: hydrophilic and hydrophobic. Effectively, the water phobic are the ones that will come together naturally and form effectively the membrane. The hydrophilic heads protrude out and protrude in, and from then all of these wonderful attachments begin to occur. Whether they're proteins, sugars, combinations of that, sugars and fats, all the different things that are there. Yes, there's other things that are there. So sometimes you'll have lipids on the inside and sugar groups in the outer membrane, fine, not a big deal. So I'm not worried about glycolipids. Cholesterol, by definition, increases membrane stability. The proportionality of it is not significant for us at this point in time. So there you go. It just naturally they form these things. So you've all seen this type of thing. There's nothing further to discuss about it. That's there. It's all about, I spent all that time folding the stupid things, trying to tell you about all these proteins. You've got to understand, they basically dictate what this cell is about, what goes in, what goes out, okay, what the cell can do, how it interacts with others, basically, whether it's independent, which is comparatively rare, and most of them function as a unit. And as you can see, it takes up an immense amount of mass, comparatively speaking, very, very specialized, and it's meant a lot of them can move around, hence this fluid mosaic. By definition, if it's integral, it's part of the membrane. If it's peripheral, it can protrude in or out. And most of the proteins are a combination. So they have the ability, if they are contacted on the outside, to make an alteration on the inside, as you will begin to see. There's so many examples. It's not, in living systems, there's not a lot of simplicity. There's usually, sometimes they're fairly simple, but most of these things cause a variety of changes. So integral proteins span the membrane. The whole idea, that whole folding thing that was going on, is to give you an idea where this was and what they can do. Okay, yeah. Channels and carriers. Channels basically indicate they're usually open. Carriers typically indicate that there are different, they may or may not be open. Channels have some specifics. You're going to get sick and tired very, very soon. Probably starting, I don't know, in a month, about hearing about different kinds of channels, leakage channels, gated channels. You'll actually hear about it sooner than that. Okay, all of these types of things, ligand gated channels, chemically gated channels, voltage gated channels, all because there are different things that open and close the channels. Maybe that's the best way to express it. So that's coming. The peripheral proteins, yeah, all the stuff, enzymes, change shape, all of these types. These are the myriad of roles that are there. Hard to read that, not going to effort, but they fortunately do them individually. They have animations that are useless on this, unfortunately. Usually their animations are very good. These, if you want to look at them, feel free to look at them on, on whatever vehicle you're using at home. I assume these are compatible with Mac, and they're compatible with, with PC systems. I usually use PC systems. My wife kind of lives on her iPad. So, first of all, transport. Again, the difference between really something that adapts to shape or something that's open. So basically a transport protein all the way across, very specific as to the solutes. That's a really significant feature. Don't forget to grab the attendance sheets, moving around as you come in. Thanks for coming. Okay. I mean that. I'm happy to have you people here. So nevertheless, it's very specific. Most of them are about water. Hydrophilic, these are items that are incompatible with the membrane. And so depending on really the size, if you will, it's very specific. It's not always water. You're going to see channels that are always open for potassium and sodium in nearly every cell. Sometimes they will change shape to accommodate. Just the very act of one of these things coming in close proximity will cause a shape change and alter this channel. It'll render it from closed to open or open to closed. In the case of when we have to move against certain conditions, and we'll get to this with movement against membranes, the whole principal basis of this, and we're going to touch on movement of membranes, I would suspect today, has to do with concentration gradient. We are, thankfully, a good example today, we're packed. So anybody who comes in, they're limited seating because they want to sit far in the back or in the corner over here or right up front here. Limited seating applies. So you have to go where there's more space. That's concentration gradient. Higher concentration to lower concentration. So sometimes when we go against that force, against that amount of molecules trying to get in our way, and we're trying to escape against that, very difficult. It requires expenditure of energy. That's for ATP. By definition, you will see we call these a pump. If it is active transport, the term pump, proton pumps, commonly you'll hear about, that means energy. Down the road, you'll see when we open and close membranes, energy. Biologically, we try to conserve energy the best way we can. So if we expend energy for one thing, we'll hopefully get something else to move as well. Yeah, make sure that sheet gets around to the gang over here. I don't want them to feel left out. Nevertheless, this is signal transduction. This is the role that insulin would be the best example of it, but anything, growth hormone, almost any chemical that impacts health do this. So you have effectively an analogy here. So this was supposed to come in. You can have some kind of response. Effectively is the nature of those proteins do it. They're there. So when this and whatever it doesn't necessarily have to be a protein being the messenger, but whatever it is, insulin is just very, very large. There's no way it can get through here. It contacts one of those peripheral proteins because they're all attached in integral protein and peripheral protein from the top to bottom of the illustration. Effectively, it changes its shape. So something contacts in here, touches me, and all of a sudden I do this, I kick. That kick sets off an intracellular chain reaction. That's how insulin works. As you see down the road when we look at this, and you look at this in AP2, it triggers a pathway called tyrosine kinase, and basically kinase kinetic energy activates things. That's something just to give you some context. You don't have to know about tyrosine kinase now, and probably not ever. But changes in shape and a chain of chemical reactions in the cell. That's a classic example. With insulin, one of them is it opens one of those neat little passageways to let sugar come in. So, show you a picture. Enzymes. Brush border enzymes. Your gut, small intestine. That whole lactose thing, effectively in the tiny cellular extensions that you'll come to know are called microvilli. Did you look at microvilli when you were looking at over in lab and looking at different kinds of tissue? Microvilli mean little fingers. And so the gut is all about surface area. And so the cell, if this is the top of the cell, it's got tiny little fingers projecting, and there's epithelial cells all along it. All of them make enzymes and release them. So up comes, assuming you're not lactose intolerant, up comes, you had an ice cream cone, moment for ice cream cones. All of a sudden it comes here, and the lactose in it is broken down into glucose and galactose and absorbed. Okay, so they catalyze, fancy term. Okay, and you can see it over here. Nothing else interesting with that. Again, and it doesn't matter which, we call them glycoproteins. And indeed, all of the sugars that protrude, every cell, every living thing, its cells have sugars that protrude. They are short chains of carbohydrates. Effectively, they give it an identity. There's the classic example, I've told you this before, is my A positive versus whatever your blood type is. Why are they not compatible? Okay, your immune system is constantly active. What you will learn is that in the first 6 months of your life, your immune system becomes very familiar. By the way, if you didn't know it, your mom's immune system provides antibodies and immunological agents that cover you until your immune system develops that first 6 months of competency. It's a process called self, non-self. And so all those cells do, those white blood cells do, is they roll over continuously. There's no directionality to it. They don't know where they're going. It's a cell. It doesn't have eyes. It's just an assortment of chemicals in a particular shape. And all they do is they're rolling over structures, getting familiar with those little carbohydrates, this glycocalyx that protrudes. Down the road, if there's an alteration in that glycocalyx, while they're rolling over them, they latch on and go, invader! Okay? And if it's an invader, it sets off a chain reaction that triggers your immune system to fight off the invader. It could even be a good guy. It doesn't know. That's part of what goes on. So for people, I think a lot of talk about immunizations. We cover that mostly in micro. Effectively, what happens, some of these invaders can get to you so quickly that by already having this and encoded in our body's immunological hard drive to fight off the invader, whether it's something common like measles or whether it's something more exotic like COVID. But I have a different philosophy on the need or not need for those things. That's an entirely different lecture. And we touched on that a little bit when we talk about micro and the pros and cons of vaccines, which are very topical today if you're keeping up with the news. So nevertheless, that's the difference. A couple of little alterations in those carbs makes me A positive, maybe you O neg or you O positive, and why we're incompatible. And believe me, it's vicious. You'll learn about that. That's a discussion of the blood in AP2. That's there. But it's always the best example. Everybody's familiar with it. Cells don't function, with rare exceptions, white blood cells and red blood cells, as individually. They basically are a unit. And they are tethered together or have the capability of communicating together. Lining cells are a sheet. They're all attached to each other. Okay? When you're looking at those illustrations, it looks like, it looks like a little number of cells that are there. That's fine. And they're all attached. You don't get the three-dimensionality of it. So you think of your lungs, the openings in your lungs, the air passageways are like balls, like hollow balls, and that whole lining surrounds it, not in a linear fashion, but in a three-dimensional fashion. Like on the inside of if you opened up a rubber ball that you were playing with as a kid, the lining would all be there. Those cells are kind of like the interior of what we would call a puzzle ball, if you're kind of like jigsaw puzzles. Nevertheless, connective tissue is just that. The cells aren't tethered to one another. They have fibers. And so pulling and tugging on those fibers creates, forces. And there's adaptations to the forces. So the cells are still, maybe it's telling one cell, oh, wait a minute, we need more fibers because we're under a lot more pressure and they generate more fibers. It'll change. You learned about these terms in lab, fibrocyte to fibroblast, right? Something's got, but when I'm pulling into, I got to cope with that. Like another one. And you looked at skin, right? Remember the layers of skin, stratum basal, stratum granulosum. See, you guys did learn something. Okay? He's probably going to test you. Did he already test you on that? What? Oh, good. I hear you. Bones practical. I get rite of passage. My students are having it next week in advance. So remember they told you about the stratum spinosum? It's not like, the membrane all of a sudden got little spiny things, got spikes on it. Frankly, it's an optical illusion. It has to do with the staining and the preservation process. If you know your way around and been doing this for a long time, it's a field called histology. We studied it. Effectively, they make you think the cells are connected. I spare no expense. It's like this. When they're attached to each other, it's going to make the cell look like it's changed. Oh, it's got a sharp point. Living systems have very few sharp points. Everybody. Thank you. With my dog, always have one handy. Why don't you bring your dog to school? There aren't enough of these. Just letting you know. Our other dog, who died, we had to put to sleep about 4 years ago. I mean, it was hard to walk because he just kept going. Everybody adored him. So that's the idea. They're connected. How are they connected? Extracellular attachment. How are they joined? They're joined by these proteins. These are the cell adhesion molecules. A fancy name we call them is CAMs. You're going to see there's 3 divisions of those. That's really the crux of what I have to tell you about that. Here are the sugars protruding. The nature of that, having an organic molecule, provides all the things, the identity, the ability to adhere, but also the ability to attach other things to it. So what you will begin to see, certain cells have more of these than others. And down the road, when it becomes relevant, we'll talk about what they mean. But again, the so-called glycocalyx, sugar shell, sugar coating, biological markers, immune system, self and non-self. Very interesting little clinical nugget. So the whole way when we make what are called killer T cells, the way we fight cancer, the trouble is the cancer keeps changing. And all those little markers change. And all of a sudden, the cell that we're made to fight it, that's why everything biologically, everything in clinical practice when someone is sick, whether it's antibiotics for an infection, whether it's cancer, early identification and treatment. You've got to get ahead of it, because if not, it will get ahead of you. That's why many of you going into clinical fields, when people come to you, if they think they have a problem, they have a problem. There's a lot of that, let's wait and see what happens in the morning, is not necessarily a good idea. Maybe they have a tummy ache, that's fine. And even then, you're worried about things like appendix. So this is the part, and this is the very last part for the first exam. There are a limited number of cells, and sperm cells probably don't even qualify as a cell. I think white blood cells and red cells are probably the best examples. 3 kinds. All you have to know is what the 3 kinds do and the 3 names that are there. The only thing I will add to the party is that when we come to gap junctions, another term for gap junctions you'll see in the PowerPoint, called connexons. Connexons are the equivalent of a gap junction. That's how cells can communicate, by sending chemical or electrical signals by way of charged particles to one another. You'll see that. You'll see ample evidence of that. Particularly, when you struggle, you probably looked at bone a little bit. When we get into bone, it's how bone cells kind of tell each other what to do. Not the only cells. Tight junctions, watertight. The more of those you have, tether the cells together, the less likely things can get in between the cells. Desmosomes, the strongest, almost like riveted together. Gap junctions, intracellular communications, or connexons. So that's part of this little thing. So tight junctions, adjacent cells, impermeable. The more of these. I mean, I used to have it. I keep forgetting to bring it in. Is if you had one staple on this, they'd be held together, but almost anything can get through. If I had a staple here and a staple, you just turn reports in, staple, 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 and you turn them in. That's great, but surely stuff could get in between the staples. So imagine each one of those tight junctions is a staple, and if you took a stream of staples, it would be very, very difficult for anything to pass through it. It would almost be like you bound it or laminated it or put one of those plastic neat things to submit the report. In the old days, everything was paper and hard copies. Effectively, that's what a tight junction is. You're going to see in certain areas we have a barrier. Your brain is the best example. The lining cells in your brain, in the capillaries in your brain, are filled with tight junctions. It's called the blood-brain barrier. In your stomach, okay, to prevent the acid from getting through, tight junctions. What happens when someone they drink too much, if they eat harsh foods and stuff like that, over time they can develop a thing called an ulcer. What happens with that ulcer is it takes away and begins to destroy that barrier. And eventually things can get in and destroy the underlying area. Because an ulceration think of it as a defect in that lining that can be very, very substantial. People can die from those. So fluids and most molecules from moving in between cells. Some areas in your gut, it's designed that way. We allow molecules to move in between cells. It all depends on what the molecule is and how problematic it might be. So here, those are the aforementioned things like microvilli. So they're kind of showing you that's those little fingers. And so if you have these little gaps, okay, potentially those little gap spaces may be a way for things to pass through. They're showing you all 3. Tight junctions are sort of like, think of a belt around each cell, and the belts are kind of belted together themselves. Okay. Here are the desmosomes, very, very strong, as you will see from the diagram, which is molecularly pretty accurate. And here are the connexons or gap junctions, as you'll see also. So the desmosomes rivets. It's like when they're building a skyscraper, and you're up there. It's amazing how people can climb up there and rivet those steel girders together. And that's, I mean, I grew up in the New York metropolitan area. You're seeing buildings going up. How can people climb on those things? I'm afraid of a stepladder. And I'm claustrophobic. I do not like to get on a plane other than absolutely necessary. Since I really don't drink, it's awful. I mean, I'm like, please let me out of here, please. My wife hates traveling with me. Don't shut up and stop whining. I'm going to hit you. About right. So there's different, you'll see them. It's like a zipper, neighboring cells, plaques, basically reinforcing it, keratin, structural protein reinforcing it, but yet there's allowed to be give. Like in between, your heart's a wonderful example of these last two. Cardiac muscles have a very interesting area that you'll learn about called an intercalated disc. We don't even touch on it really here in AP1. We look at skeletal mostly and a little bit about smooth muscle. And what happens is the cells have, because your heart's constantly moving, there's a tremendous amount of force. If there wasn't some give, it would tear. And your heart beats, and I'll say it a zillion times, more rapidly than once a second every second of your life. So how does it stay together? There's a certain amount of give, but there's so much strength with these desmosomes. At the same time, those connexons are, if one cell fires, then the next cell has to fire, and then the next cell, and the next cell. How do the signals pass to know, okay, it's your turn? It's like a series of dominoes. You flip one down, and it all goes in a very organized pattern. It's kind of what your heart does. Except rather than falling and not being, it just stays upright, but it signals from one to the other. So all of these types of things, it doesn't tear. So that's the idea. I mean, this is really what the construct looks when we look at it under, when we're able to look at it molecularly and under, significant degrees of magnification or electron magnification. Proteins that link them together, plaques, keratin fibers, all of these, they're called intermediate filaments. We're going to get to those when we talk about the cell. And then here are these transmembrane or connexons, tunnels. They're tiny openings. DNA and RNA. The way RNA can exit the nucleus is by these openings that are really a variation of a cap junction, a bigger part of a gap junction, because it's large enough to let molecules go through. We call it a nuclear pore. It looks very much like this. So even though that's a large molecule, you can imagine it's just a larger opening. But typically the communication are smaller processes, mostly charged particles. So cardiac and smooth muscle cells, absolutely. Typically you're looking at calcium and potassium. When you get into the heart unit in AP2, you learn more about that aspect of physiology. Believe me, you'll get sick and tired about hearing. That's why, and I say it to you multiple times, things that doctors get excited about when they see irregularities in calcium and potassium. If somebody's potassium goes low, it's not like, well, we'll give you some potassium pills, which are yucky, by the way, and see you in the morning. No. That's a right away. And there's nothing more unpleasant than having an intravenous with potassium in it. It's burn. Many of you, if you're in nursing, you're going to find that out when you have to hang potassium. Patients are not going to love you. This is burning. Oh my God. It hurts. I've had it. It hurts. So here's what they look like, these little openings and channels. So they give you all three that are there. Constantly move across the plasma membrane. Some molecules easier and some are not. This is the whole idea of selective permeability. And indeed, once we finish that last slide, that concludes the first exam. Congratulations, we are done with the first exam material at 9:30 in the morning here on Friday, September 19th. Aren't you happy? I'm not giving you the test next week when you have that monster thing with, do that. Sorry. It's National Test Day. All my students, I get the same day with the test. Bring in a good book to read. Something like that. It's typically what I do. And I'm in the middle of the new Dan Brown novel. Very, very well done. So. Da Vinci Code, is it ringing a bell? Some of these, he comes out with a new book about every 3 years. But he researches them very, very well. I mean, some of it's a little offbeat, but how else can I describe it? So now, What is this all about? Moving stuff in and out. So today we're going to look at passive. We do passive a lot because we don't want to waste energy. Indeed, we'll spend energy to try to push molecules and create what we call a concentration gradient. If we spend a little energy, we can actually magnify the effects. So we're very frugal with our use of energy. So today we're going to talk mostly about passive transport, and next time on Monday we'll talk mostly about active. This is all about really the most important part about learning about all those proteins, the topic of movement across membranes. So what are the three major forms of this? Simple diffusion. And the only thing about facilitated diffusion means the doorway was not open, and effectively by some way, shape, or form we have enabled the diffusion to occur or facilitated that. I mean, again, that's what insulin, one of its many roles, is facilitates the diffusion of glucose. And again, lastly, the movement of water. Most cells have pores that allow water to move. So right away, terminology becomes significant. So when we're talking about glucose, we're talking about solutes. So whether it's calcium or potassium or glucose, any of those types of things, sodium, boron, whether it's charged particles or small molecules, collectively refer to them as solutes, stuff dissolved in the water. And solvent, that's for our purposes. But you can't just, your mindset has to understand that everything has the capability of moving and following the single most important factor, which is concentration gradient. When you have a lot of people in an area packed together, potentially they're constantly bumping into each other. Molecules are no different. Okay? And as they're bumping into each other, they tend to be pushed toward open spaces. Just the way, again, if we had half a dozen more people coming in, where are they going to go? They're going to have to go to the areas where there's still space available in this classroom. It's just the way it works. If you're going into a theater before they had, now you can pick your thing and all that type of comfortable chairs, like the fact that they recline. And going to movies is a ball. This is even better than being at home. It didn't used to be like that. But nevertheless, the whole idea of that was you would go to different areas. So, and that's why there's force in concentration. You try it sometime. If you're going to the next time the Steelers are at home, which won't be for a while, okay, if you're in any venue like that or a Penguins game, in between periods, you don't want to be the one who's pushing against that crowd that's going out there to either go to the bathroom or go to the concession stands or wherever they're going. If you're pushing against them, you're going to spend a lot of energy to get back to your seat or wherever you're going. Just the way it works. Or you can ride with it. Heck, you got halftime in a big football game with 60,000 people. You can just get up and the whole crowd will carry you and I'm getting over the bathroom. Okay. Right? It's like the force of the flow. That's the idea of concentration gradient. Okay? The whole idea. So simple diffusion, facilitated diffusion, and osmosis, the one that students hate. Because for the time being, when we talk about simple and facilitated, we're talking about solutes. And understand, even gases like oxygen and carbon dioxide effectively are solutes. And many times they are dissolved in the solvent of water. But for our purposes, they effectively work like a solute. So all molecules, random high intrinsic kinetic energy, they move resulting from collisions, higher concentration, lower concentration, yeah. Small things travel faster, temperature increases it, blah, blah, blah. Everybody's done that thing somewhere in a classroom where they got a beaker of water and stuck something in it, like a blob of dye or whatever, and hey, watch it spread. Okay. What do you see with blood? Here's something to give you an idea about a thing. Why you don't get excited when you see a lot of blood sometimes. thimbleful of blood will make a gallon of water turn red. What? You get a whole thing of gauze pads, and you put a drop of water. About a couple of gauze pads later, they're dry. Put blood, go all the way through. So people get kind of excited because you'll get people who have, quote, blood in their urine. And I mean, typically there's just a little bit of discoloration. When somebody has urine that's red, peeing red, not a good thing. Unless there's a really good explanation. Like I was in a football game and I got hit. And all of a sudden, okay, we can understand that. Maybe some cells were damaged and hopefully it's just transient. It's the number one reason why somebody pees red. Anybody? Bladder cancer, which I had. Number one reason why people get bladder cancer, smoking cigarettes, which I only did for 40 years. None of you have smoked for 40 years, I would dare say. I don't think anybody here is 40 years old. 2 packs a day, 40 years. Didn't I tell you that? I didn't. Okay. 40 years, 2 packs a day, roughly from when I was end of high school, start of college, till 2008, June 20th. And I have been smoke-free ever since, which is I'll give myself a pat on the back for that. Price I paid, not lung cancer, bladder cancer, which thankfully is, as far as we know, gone. I'm doing good. I behaved myself. That's why you don't want to have children. My son and his buddies, they like to smoke cigars occasionally when they're on the golf course. Or, I mean, he was doing it last night. We're having a bourbon and cigar thing. He's up at the Naval War College in Newport. And so he's like, oh, Dad, we got cigars. You want to come down? No, thank you. Never again. Too hard. So much for me. Here, concentration, size, temperature, big factors. All things, and it doesn't stop. When you have particles on one side and they move, and particles on the other side and they move, it's like magically, okay, we're equal. It's like the movement doesn't stop. Equilibrium means there's always a particle going this way and always a particle going. It's just the way it works. This is a living system. We don't have standstills. Living systems, there's constantly movement of molecules. So the reality, and it's well explained, it's the net movement. Once we have effectively as many particles on one side as the other, and they continue to move back and forth, but the net movement effectively equates to zero. That's the idea. Living systems don't stop things moving around. And so, again, you're going to see where this is when we start talking about how things move out in the cell. I'm preparing you for a difficult topic called resting membrane potential, which is so important because everything is based on that. So non-polar, hydrophobic lipid core of the plasma membranes don't allow water-soluble things, even small charged particles, to get through. So it creates these permeable barriers depending on what it allows to go through. Only things that can get through the membrane are very tiny, or they're fat soluble. Even something like cholesterol, okay? It looks like a big molecule with those 4 carbon rings. It's relatively tiny vis-a-vis getting in and out of that membrane. And indeed, it forms in that membrane. So lipid soluble and non-polar. So lipid soluble would be cholesterol because it is a lipid. Non-polar, oxygen and carbon dioxide. And so the very small molecules that can pass through membranes or membrane channels refer to as simple diffusion. For our purposes, we look at things that are typically non-polar and small lipid compatible molecules that are there. Water is the oddball, that's osmosis. So when it involves a particular carrier that allows particles that don't meet this, larger or polar charged particles, non-lipid soluble, okay, facilitated diffusion. And osmosis is the movement of water. So that's the base for all of this. So you all had skin. You all talked about burns. The 2 major problems that somebody has with a severe burn, I'm not talking about a little burn, a sunburn or something like that. the big problems when there's a significant burn are twofold. Initially is this: substances, we lose the integrity of the skin, fluid. So fluid and electrolytes is worry number one. Okay? Burn patients, movement of solvent, usually water, very, very much a problem. I beg your pardon. Movement of mostly water and all the particles that are in it. Okay? So I want to get back there. Substances diffuse freely into and out of the cell. Okay? Burn patients lose all of those things. Okay? And that, even somebody with second-degree burns, which are we call partial thickness burns, that involve blistering. That's the definition. In the old days, we call them second degree. Now they call them partial thickness. And I mean, somebody with a lot of those is in big trouble. We're not even talking about full thickness or third degree burn. They're in big trouble. So that's worry number one initially. Number two, problem with burns, infection. Burnt tissue is comfort food for bacteria. So you're always worried. Those are 1 and 1A. First, fluid and electrolyte balances. I mean, so in the process of giving you an idea clinically about these things, just like in the movies. Okay. First Christmas night I worked in an emergency room. My first wife and I, since we're both Jewish, always we'd work Christmas and Easter because that's the folks who want to celebrate with their families at home. It was just us, the two of us and the dog. That first night, nothing was happening. It was church mice, 2 to 6 o'clock, from 2 p.m. to 6 p.m., nothing going on in that place. At 6 p.m., everything went wild. A flop house. If you don't know what a flop house is, it's where homeless individuals paid 50 cents at that time. Back low, this 50 years ago, this was Christmas of 1977. They paid 50 cents, they can have a bed. It was so cold. I mean, we're talking about wind chills and freezing temperatures. Awful. The flop house caught fire. There was maybe 100 men. It was a man's flop house or more, who were all, engulfed in flames. All the area hospitals. This was 2 blocks away from our hospital. They sent it to our hospital. They sent it to another hospital farther away. This was in North Philly. Not a particularly great neighborhood. Okay. That was there. Temple University Hospital was way up a couple of major blocks up the road. The downtown hospitals were a couple of blocks in the other direction. We were a small 200-bed hospital. We had, I would dare say, 50 to 75 because we were the closest. We lost 2 in ER and 2 in ICU. Because you're talking about homeless individuals who are in poor health to start. It's there. That's when I learned to start IVs, because the attending, and we were on a skeleton staff, and all of a sudden we went from full-blown to full-blown disaster. All of a sudden, we got people in there. We got to put 2 IVs into everybody to run fluid. So as soon as they get in here, I want 2 wide-bore IVs in their arms. And I'm like, ugh. He says, well, I really haven't been a whole lot successful. You'll learn now. Do it. And it doesn't matter. You got to get the fluid in. I learned real quick. Bloody a few of them, and boom, boom, all of a sudden I'm the IV pro. Used to call me up to start IVs on drug addicts. I got to be so good at it. At the same time, I learned we didn't have that neat little pulse ox thing. We had to do arterial sticks to get it out of the right artery. Not so easy to do. I learned to do those really fast. That just gives you an idea. It was absolute chaos. That's there. If you watch that, the wonderful show, The Pit, on HBO, if you get a chance to watch that, it's just brilliant. They showed you that happen with a gunshot. All of a sudden, you have a disaster with multiple injuries coming. In this case, multiple burns. It happens all the time. It's not just me. Anybody who worked in an emergency room will give you the same kind of stories. I just want to give you some context why this stuff is so important. So we only have a chance here to do the first one of these. Let me do them up. Simple diffusion. The 2 ingredients are called, heard their names before, oxygen and carbon dioxide. They aren't gases. In your lung, you have a common base plate or basal lamina. We used to call them a basement head. Little ring of protein. On one side, you have blood vessels. Here's epithelia. I love epithelia. Simple swing. Because all it's designed is just basically nucleus, it's like a fried egg and a whole bunch of membrane. On the other side, they share a membrane. You have in your lung simple squamous, and here in capillaries. You have more simple. The beauty of simple diffusion, you have a ton of oxygen here. Just breathe in, and a little bit of carbon dioxide. Here you have a ton of carbon dioxide, a little bit of oxygen. There's no oxygen in those red cells. Actually, they won't lose much. What happens as soon as they get to the area, fraction of a second, that's when they take the blood out of you. You take blood out of somebody in a vacuum chamber. It immediately it's got a distinct red color that's normal looking. Believe me, in that vein, it's a little bit more bluish. So immediately what happens, the oxygen goes this way and the carbon dioxide goes this way. It's not like I have oxygen, I get to go first. Carbon dioxide, you have to wait. No, it's simultaneous movement. That's the beauty of simple diffusion. Multiple things can move in at the same time. And that's the beauty of that particular, and the perfect example is your lung, where you can go down to the tissue level when we have respiration at the tissue level. They show you the picture, you don't have to worry about it, I don't care. I don't think there's a whole lot there. So here you go, like this, simple diffusion, lipid soluble through it. That's what happens. You'll see that. I'm sure one of the things that you really focus on when you look at simple squamous epithelia is where it's all over the place. But the particular area where it does that job very well is there, and then they're also in the kidney to a certain extent. But the lung is paramount. That's why your blood only has to go through there for a fraction of a second. Yet it takes about 3 seconds to get all the way through all those capillaries. It's oxygenated right away. That's what I mean by redundant systems. That's the tragedy of people who were idiots like me, who didn't stop, who weren't as smart as I was and stopped smoking, thank you to my wife, okay, for compelling me. And all of a sudden, they lose that ability. And it's like this. We have so many backup systems. You can breathe for 70, once you have even as much as just 25% of your lung function. Once you get below that, all of a sudden, you go to the doctor and they say, you have to be on oxygen for the rest of your life. You've all seen them, in the grocery store, supermarket. What do you see them in the casino in the smoking session? It's like, what the? A cigarette with oxygen. Are you crazy? It's okay. That's what I mean by addiction. Goodbye. Have a wonderful weekend. Nice chatting with you. Please, as you start to have questions on the test, feel free. I will, if I have some time watching the great grandson, I will try to record a review recording for you. So if you hear a baby crying in the middle, tell Jackson, I can't hear it.